great physicist Ernest Rutherford, working in Manchester in 1910, evolved his theory of the nuclear atom from experiments on the scattering of alpha particles by thin metal foils. We're going to reproduce the classic experiments. We shall use americium-241 as our source of alpha particles. They're emitted from here. The source is mounted in this chamber. Alpha particles stream off from here. This is a solid-state photodiode which can detect alpha particles. It's connected to an electronic counter. This is a collimator ring mounted between source and detector. A gas-tight lid can be placed over the chamber. With air at atmospheric pressure in the chamber, no alpha particles reach the detector. They're stopped by multiple collisions with air molecules. Here's the counting and timing apparatus, and as you can see, no alpha particles are being registered. The air is pumped out of the chamber. There comes a point at which many alpha particles can reach the detector, and the counter shows the rate at which they're getting there. This curve shows the pulses produced by the particles reaching the photodiode. A window is chosen so that only the particles with this range of energies, alpha particles, are counted. On another screen, we can display the energy distribution of the alpha particles being counted. Thousands of alpha particles are registered as they reach the detector in the evacuated chamber. We now move the detector so that it's at an angle of about 25 degrees to the axis. As we've approached the edge of the collimated beam, as we should expect, far fewer alpha particles now register. We'll now make some actual measurements. First, with the detector in line with the source. The counter's set to count the number of particles in a certain time interval. The time interval can be displayed in units of 1/10 of a second, so that was 500 tenths, 50 seconds. Now the detector's at 15 degrees. A small count. In the same time interval. 125 degrees. Far fewer counts. No counts in 50 seconds at 30 degrees. (135 degrees). Two counts in 800 seconds, a small background count. We now put a piece of thin gold foil in position, mounted on the aluminium disc. The foil's only 1 micron thick. Any alpha particles reaching the detector must have passed through the gold foil. So in this position we'll see how many alpha particles go straight through the gold foil. In 50 seconds. (15 degrees). Far fewer at this angle. Even in 2,000 tenths of a second, 200 seconds. Fewer still. We're now going to look for alpha particles scattered back off the gold foil at 135 degrees. Now, even though most of the alpha particles go straight through the foil, some have actually bounced back. Rutherford developed a theory to explain what was happening. If atoms have small positive central nuclei surrounded by a cloud of electrons, many alpha particles will go straight through the foil. This is a diagrammatic out-of-scale picture of the process. The nuclei would be much smaller proportionately than this. Some alpha particles, passing near the positively charged nuclei of the atoms in the foil, are deflected, like this. and just a few alpha particles will go so near the tiny nuclei that they bounce back at this sort of angle. While a very few alpha particles indeed will score direct hits and bounce straight back. The scattering takes place as it does because of the nuclear nature of the atom. We're now going to measure scattering by 4 different foils, each at 30 degrees. First, a thin gold foil. These very thin foils are easily damaged, so you have to be careful with them. Each count will be for 200 seconds. This is the count for 200 seconds. Now a silver foil. In 200 seconds. A thin copper foil. From these readings, it's possible to relate the scattering of alpha particles to the atomic numbers of the elements comprising the foils. This is cling film, thin polyethylene, which will give us the scattering from carbon atoms. You can use the experiment booklet to interpret all these readings, and also the further readings given in the booklet. For 200 seconds again. Finally, another interesting application. This shows the energy of alpha particles scattered by gold foil. This is for silver foil. The peak moves left to lower energies as the mass number decreases. We can use this technique to detect what elements are present in thin films. This is for copper. And carbon, in polyethylene film, gives us a further shift to a lower energy peak. The notes in the experiment booklet will help you interpret the results of these experiments on the Rutherford scattering of alpha particles.